Okay, I hope I'm audible to all the students who are attending this lecture of Introductory Econometrics. We continue with our lectures on linear regression. And in the last lecture of linear regression, we had looked at the non-stochastic population regression function. If all of you can recall, we had started with the regression analysis in the previous lecture, which looks at the study of relationship between the dependent variable, also called the explained variable, as well as one or more variables called the independent or explanatory variables. Okay, so we had done this quickly. I am writing it. Recall regression analysis looks is concerned with regression analysis is concerned with the study of the relationship between the explained or the dependent variable and one or more variables called the explanatory variables, called the independent or the explanatory variables. Okay, and then guys, we had done the case of population regression function. Okay, so we had done in the last lecture something called deterministic or non-stochastic population regression function. Deterministic or non-stochastic population regression function. Okay, so if you all can recall the underlying theory behind this, for every value of the independent variable x, we have lot of values of y. Quickly drawing the diagram which we had drawn in the previous lecture as well. For every fixed value of x, say x1, x2, x3, and so on, I can go on till xm. We have lot of values of y. So I can say for every value of x, y itself is a random variable. For every value of x, we have lot of values of y. Okay, and what are we interested in looking at? We are interested in looking at the average value of y or the mean value of y conditional on a fixed value of x. So suppose when the value of x is x1, the mean value of y is this. Suppose when the value of x is x2, the mean value of y is this. Suppose when the value of x is x3, the mean value of y is this, and so on. So when I join all these points, I can stretch it, guys. When I join all these mean values of y conditional on the fixed values of x, I get the population regression function. So how did I write the non-stochastic population regression function? Expected value of y conditional on x taking a particular value xi is equal to b1 plus b2 times xi. This was the population regression function which we had done. Why is it deterministic? The reason that this population regression function is deterministic is because if you look at the right hand side, we know b1, we know b2, and xi itself is non-stochastic. X is a non-stochastic variable. Non-stochastic variable means it does not have a probability distribution attached to it. It is taking fixed values x1, x2, x3, dot, 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 xn. So it does not have a probability distribution attached to it. On the other hand, guys, y is a stochastic variable. Why is it a stochastic variable? Because it itself has a probability distribution attached to it. And I can stretch it forward. If I erase this particular part, I can stretch this population regression function forward. So it will look somewhat like this. This is going to be my straight line. Okay. This particular point is expected value of y when x takes the value x1. This particular point is expected value of y when x takes the value x2. This particular point is expected value of y when x takes the value x3. And I can stretch it and I can write this is expected value of y when x takes the value xm. So you can see it's a straight line. It's a linear line. Every linear line has two particular parameters. One is called the slope parameter and one is called the intercept parameter. So the slope parameter of this regression line is B2 and the intercept parameter or the intercept coefficient, slope coefficient or slope parameter is B2, intercept coefficient or intercept parameter is B1. Okay, in the last lecture we had also looked at the interpretation of these regression coefficients. So guys, B1 and B2 together are called the regression coefficients. Together they are known as the regression coefficients. B1 is the intercept coefficient and B2 is the slope coefficient. And guys, in the last lecture we had also done the interpretation of B2. Okay, so if you all can recall, how do we interpret B2? So we had done this in the previous lecture. It is a revision in this lecture. Interpretation of the slope coefficient B2. Interpretation of the slope coefficient B2. So we can write B2 measures the rate of change. B2 measures the rate of change in the conditional mean value of y. Conditional mean value of y per unit change in x. B2 measures the rate of change in the conditional mean value of y per unit change in the variable x. Okay, and for simplicity, if all of you can recall, we had done this in the previous lecture that throughout the entire linear regression lectures, for simplicity, I will be writing expected value of y given x equal to xi as expected value of y. This I will be writing for simplicity. So the population regression function will give me the conditional mean value of y, or I can say in another words, I can say that the slope coefficient B2 will give me the rate of change in the conditional mean value of y per unit change in the variable x. And the population regression function will give me the conditional mean value of y for every fixed value of the variable x. Okay, all this we had covered in the previous lecture. Now guys, in this lecture, we look at the concept of stochastic population regression function. In the last lecture, we had done the concept of non-stochastic or deterministic population regression function, where everything on the right hand side of the regression equation was deterministic. We knew B1, we knew B2, we knew xi. But now in this lecture, I am going to define something called the error term. the error term, or also called the noise component. Okay, so guys, we can say for each I going on from 1 to m, define the disturbance variable, or the error term, as. So guys, we are now defining the population error term, or the population disturbance variable, or the population noise component as ui. Now ui is nothing but the difference between the actual value of y when x takes the value xi and the expected value of y. So the error term is nothing but the difference between the actual and the expected value of y. Now guys, if you all can recall, what was expected value of y? Expected value of y was itself equal to b1 plus b2 xi. We had done this, right? Expected value of yi was equal to b1 plus b2 xi. Okay. So we can write that is the disturbance variable. The disturbance variable is the deviation of the actual y from its mean. So guys, how can I write this above this equation star? So therefore we can rewrite equation star as yi is equal to b1 plus b2 xi plus ui. And this is called what? This is called the stochastic population regression function. This is known as the stochastic population regression function. You can clearly see, guys, that in this case, b1 plus b2 xi, this is the systematic component. This is the systematic or the deterministic component. Of the stochastic population regression function. And ui, what is ui? Ui is the non-systematic. Or also called the random component. Non-systematic or the random component of the stochastic population regression function. So in the last lecture, when we had done the non-stochastic population regression function, it did not contain the error term. Everything on the right hand side was deterministic. But in this lecture, when you all are looking at the stochastic population regression function, clearly it also contains the disturbance variable or the error term. It is the difference between the actual y and the expected value of y. So ui is yi minus b1 plus b2 xi. Okay, we can rewrite the equation like this. Yi is equal to b1 plus b2 xi plus ui. Okay, now guys, this I can write like this also. So I can write therefore yi is equal to, what is this term? This term is expected value of yi. This is expected value of yi, which is systematic or deterministic, plus the random error term ui. So I can write it like this. I can write my stochastic population regression function like this. Yi is equal to expected value of yi plus ui. So guys, understand this. Ui is also stochastic. because ui itself has a probability distribution attached to it. In the entire regression which we have done till now, there is only one variable which is non-stochastic, and that is xi. Yi is also stochastic, ui is also stochastic. That means both yi and ui have a probability distribution attached to them. Only xi takes fixed values. It is non-stochastic. So guys, let's further dig deeper into the error term. So we can quickly go through some of the assumptions. So assumptions of, so I can write about the disturbance variable, or the noise component. Assumptions about the disturbance variable or the noise component. So guys, in this linear regression analysis, what are the assumptions we are making? So let's look at the following assumptions. First assumption is zero mean. Zero mean, that means expected value of ui itself is equal to 0 for all I going on from 1 to m. This means that for each disturbance variable, the positive and the negative disturbances balance out. The positive and the negative disturbances balance out. So what does this mean? This means, guys, for every fixed value of x, y will take lot of values. Since y will take lot of values, ui will also take lot of values for one given value of x. So on an average, the positive and the negative values of the error term will cancel out. So expected value of ui will be equal to 0. So if you want to understand this, you can look at the diagram. Okay, so the diagram was as follows. If you all can recall, x was taking fixed values. Okay, x1, x2, x3 dot 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 xm. It was taking fixed values, if you all can recall. And for every value of x, we had y itself being a random variable. Clear? So, and we were looking at the expected value of y when we had built the population regression function. Okay, so guys, this was our population regression function. Expected value of y given x equal to xi, which was capital B1 plus capital B2 times xi. Now guys, what is ui? Now see, these dots are the actual values of y. So for x1, suppose this is my y1. Suppose guys, this is my y1. So y1 minus this expected value will be, so guys, this distance will be how much? This distance will be u1. Similarly, suppose for x1 itself, suppose my another value of y is this, y1 dash. For x1, my another value of y, actual y is this. Now guys, what will u1 be? The difference between this. You can see in this case, my u1 is positive, y1 minus the mean value. In the second case, my u1 is negative, y1 dash minus the mean value. So what the first assumption is trying to tell us, It's trying to tell us that for one particular value of x, the UIs on an average will cancel out each other. That means the positive and the negative values on an average will cancel out each other, leaving the mean value of UI equal to 0. So you can clearly see in this first case, U1 took a positive value also, U1 took a negative value also. So on an average, they cancel out. So expected value of U1 is equal to 0. Same thing I can do for x2 also. For x2, one value of y2 is this, hypothetically. So the difference between these two values is u2. And one value of y, suppose, is here, y2 dash. So difference between them is also u2. So you can see in the first case, u2 is taking positive values. In the second case, it's taking negative values. So you can again see on an average, the positive and negatives will cancel out each other. So I can say expected value of u2 is also equal to 0. And I can keep on continuing this and I can say expected value of um is also equal to 0. That means for every fixed value of x, y is also a random variable, u is also a random variable. I can write this. For every fixed value of x, for every fixed value of x, y and u are random variables. Both of them are random variables, okay, such that expected value of ui is equal to 0. That means for a fixed value of x, the error term will sometimes take positive values, sometimes it will take negative values, such that on an average, the positive values will cancel out with the negative values, giving us the expected value as 0. So I hope all students have understood the first assumption. Let's quickly look at the second assumption, which is homoscedasticity. The second assumption talks about homoscedasticity. So guys, this assumption tells us that variance of UI is a constant, where sigma square is a constant. Now, what does this assumption mean? For all I going on from 1 to n. So I can say this means that all the disturbance variables have the same level of variation. All the disturbance variables have the same level of variation. So guys, homoscedasticity means what? It means for every value of x, for every fixed value of x, the disturbance term u will have the same variance. Now again, if you want to understand it diagrammatically, so you can look at the diagram which is drawn on the screen. Again, we have the variable x, variable y. X is taking fixed values, x1, x2, and I can stretch it on till xm. Okay, you can clearly see for every value of x, y itself is a random variable. For every value of x, y itself is a random variable. So this is expected value of y given x equal to x1, expected value of y given x equal to x2, expected value of y given x equal to xm. I join this, I get the population regression function. Now guys, what are we further saying? We are further saying, okay, think about it like this, that suppose my error term ui has a normal distribution. Suppose the error term ui has a normal distribution. Then guys, you can think about if you draw the normal distribution curve, it is somewhat going to look like this. If I draw it on the screen to explain you, the normal distribution curve is going to somewhat look like this. So this is how we draw the normal distribution curve. Okay, so it is going to be like this. So what this assumption is telling us, that the spread is going to be the same. The spread is going to be the same. This is the assumption of homoscedasticity. This means what? So this means for every fixed value of x, variance of ui will be the same. Okay, variance of ui will be the same and equal to a constant sigma square. So guys, for x1, u1 will take lot of values. If you calculate variance of u1, it will be sigma square. Similarly, for x2, u2 will take lot of values. If you calculate variance of u2, it will be sigma square. Similarly, guys, for xm, um will take lot of values. If you calculate the variance of that is also going to be sigma square. That means the spread around the mean value will always be the same. What does variance capture? Variance captures dispersion. Variance captures the spread of the values around the mean value. So when we talk about homoscedasticity assumption, it simply means for every fixed value of x, the disturbance variable ui will have the same variance. It means variance of u1, variance of u2, variance of all will be equal to a fixed value called sigma square, where sigma square is a constant. Okay, so I hope that students have understood the homoscedasticity assumption. Okay, and why we have drawn this, because the assumption here is that ui follows a normal distribution. All of us should know the assumption here, and this is the assumption which we'll be making in the entire linear regression lectures. ui, which is my disturbance variable, follows a normal distribution with mean value as 0 and variance as sigma square. My disturbance variable ui is going to follow a normal distribution with mean 0, because my first assumption was expected value of ui is 0. The positive and the negative terms cancel out. So expected value of ui is 0. Variance of ui is equal to homoscedastic variance sigma square. I hope all students are clear with the second assumption. Okay, moving on to the third assumption, non-autocorrelation. This is the third assumption about the disturbance variable ui. So non-autocorrelation. Now guys, what does non-autocorrelation mean? Non-autocorrelation simply means that two different disturbance variables are not correlated. They are not correlated with each other. So I can say that this assumption means okay, this assumption means that covariance of ui comma uj is equal to 0 for all I and j going on from 1 to m, I not equal to j. So we can say this means that the disturbance variables are uncorrelated with each other. The disturbance variables are uncorrelated with each other. So I hope that students have understood the third assumption. That means for x1, my disturbance variable is u1. So I can write it. Example, for x1, my disturbance variable is u1. For x2, my disturbance variable is u2. The assumption is that u1 and u2 are not correlated. That means if you calculate the covariance between u1 and u2, it is 0. So guys, the third assumption is telling us that one disturbance variable is not dependent on any other disturbance variable. So if one disturbance term is increasing, it does not mean that the other disturbance term will increase. So what we are trying to point out in the last assumption here is that two particular disturbance variables have no correlation between them. Two particular disturbance variables ui and uj for I not equal to j are uncorrelated with each other. They do not share any correlation. Okay, so that means you cannot observe any pattern between two disturbance variables. You cannot form a pattern. Every disturbance variable follows its own trend. It's not dependent on the other disturbance variable. So I hope that students have understood and have no doubts. Okay. Now, guys, we have done the concept of non-stochastic population regression function. We have done the concept of stochastic population regression function. We have also looked at the assumptions of the disturbance variable ui. It has zero mean, it has homoscedastic variance, and the disturbance variables are not correlated with each other. So I hope all students have understood this, and you can quickly write a note in your registers. Okay, the disturbance variable itself is a random variable. The disturbance variable, which is ui, itself is a random variable whose value cannot be controlled. It has a whole probability distribution attached to it. It has a whole probability distribution attached to it. So I hope students have understood this. For every value of xi, yi is also a random variable, ui is also a random variable. And any random variable will always have a probability distribution attached to it. Also, any random variable will have mean also, it will have variance also. And we have seen that for the disturbance variable ui, the mean of ui is 0. And we have looked at the variance of ui is the homoscedastic variance sigma square. So I hope all students have understood the concept regarding the population regression function. So guys, we now look at the concept of sample regression function. Now guys, understand this. We don't know the population. Population is very large. So what are we going to do? Since population is very large, we will now be taking a sample. So from the population regression function, we now have the sample regression function. So now our heading now is sample regression function. Okay. So our heading now is the sample regression function, SRF. Now, guys, you all should know that in real life, population is very large. The population under study is very large. So usually what do? We take a sample. So now what will my sample regression function look like? So if you all can recall, my non-stochastic population regression function was, it was expected value of yi is equal to capital B1 plus capital B2 times xi. This was my non-stochastic PRF. Now, guys, in reality, we don't know capital B1. We don't know capital B2. We don't know expected value of yi because all of these are population. So now we are going to take a sample which will be used to estimate these values. So I can write the corresponding non-stochastic sample regression function. Non-stochastic sample regression function is what? So this is given by yi hat is equal to small b1 plus small b2 times xi. Now, guys, remember xi is non-stochastic. Xi is anyways fixed. Whether you look at the population or you look at the sample, xi is taking fixed values. It's a non-stochastic variable. But now you can clearly see where yi hat is the estimator of, all students have done with me the concept of estimation. In the paper Statistical Methods for Economics, we had done the concept of estimation. So yi hat is the estimator of expected value of yi. Small b1 is the estimator of the population slope, the population intercept coefficient capital B1. Small b2 is the estimator of the population slope coefficient capital B2. So guys, small b1, small b2, yi hat are coming from the sample and they are used to estimate the population values. So yi hat, which is the sample mean value of y, is used to estimate the population conditional mean value of y. Remember, expected value of yi is conditional on x equal to xi. Similarly, small b1, which is my sample intercept term, is used to estimate the population intercept term. Similarly, sample slope coefficient B2 is used to estimate the population slope coefficient capital B2. So this is my non-stochastic sample regression function. And throughout our entire lectures, we will now be focusing on the sample regression function, which will be used to estimate the population parameters. Because we do not know the population is very large. We only know the sample, which will be used to estimate the population. Similarly, guys, all of you can recall we had done in this lecture stochastic population regression function. Now, if you all can recall, what was stochastic population regression function? Yi is equal to b1 plus b2 xi plus today in this lecture we have defined the disturbance variable ui. So yi is my actual y, b1 plus b2 xi is my expected value of y, plus the random or the disturbance variable ui. Now guys, corresponding to it, what will be my stochastic sample regression function? My stochastic sample regression function will be yi is equal to small b1 plus small b2 times xi plus ei, where b1 is used to estimate capital B1, b2 is used to estimate capital B2. What is ei? Ei is the sample residual, or I can say the sample error term used to estimate the population disturbance variable, used to estimate the population disturbance variable, which is ui. So small b1 is used to estimate capital B1, small b2 is used to estimate capital B2, ei, which is my sample residual or the sample error term, is used to estimate the population error term or the population disturbance variable ui. Okay, so if I ask you guys what is ei, let's talk about ei now. Okay, so if I talk about ei, what is ei? ei is nothing but yi minus yi hat. So ei, which is this, represents the difference between the actual y values. It represents the difference between the actual y values and their estimated y values from the sample regression. Remember guys, ui we get from population regression, ei we get from the sample regression. It is the difference between the actual yi minus the estimated yi hat, which we get from the sample regression. So hoping that students have understood this and have no doubts. Okay, now guys, I want to discuss a small concept with you within linear regression, after which we intend to stop. Okay, so let's talk about the concept of linearity in variables versus linearity in parameters. Linearity in variables versus linearity in parameters. So students should be crystal clear what is the difference between them. What do we mean when we say linearity in variables, and what do we mean when we say linearity in parameters? So guys, consider three regression equations. Let's understand this using an example. Consider three regression equations. I am giving you the population regression equations. Okay. First equation is expected value of y is equal to b1 plus b2 xi. Second equation, expected value of y is equal to b1 plus b2 times xi square. Third equation is expected value of y is equal to b1 plus b2 times 1 upon xi. Fourth equation is expected value of y is equal to b1 plus b2 square times xi. Now guys, if you look at the first equation, it is linear in variable. When I say linear in variable, it means linear in the xi. When I say linear in parameters, it means linear in capital B1 and capital B2. So all of you should know this. Linear in variable means, so I am writing it here, linear in variables means linear in xi, linear in the xi's, okay, and linear in parameters means linear in parameters means linear in capital B1 and capital B2. So when I say that it's a linear regression equation, it means it is linear in capital B1 and capital B2. So guys, let's look at these equations. Equation 1, it's linear in both xi, linear in both xi and B1 and B2. But guys, look at the second equation. This is linear in B1 and B2. It's linear in parameters, linear in B1 and B2, but not in xi. Third equation also is linear in both B1 and B2, but not in xi. And if you look at the last equation, it is linear in xi, but not linear in B1 and B2. You can see B2 is coming with power 2. So guys, what does this mean? When I talk about linear regression, understand this very carefully. When I talk about linear regression, it means that regression which is linear in parameters. It may or it may not be linear in variables. So I can write it here. Okay, let me write it for all of you. So I am erasing the initial part and all students can write this note. This is a very important note in this lecture. All students will write this note. Linear regression is the regression which is linear in parameters, Guys, what are the parameters in this lecture? Capital B1 and capital B2. It may or may not be linear in the variables, that is the x's. So when we talk about linear regression, it is a regression which is linear in the parameters. It may or may not be linear in the variables. So guys, if we look at these regression equations again, these 4 regression equations, is the first equation a linear regression? Yes, because it is linear in the parameters. Is the second equation a linear regression? Yes. Why? Because it is linear in parameters, even though it's not linear in xi. Is the third regression equation a linear regression? Yes. Why? Because again it is linear in parameters, b1 and b2, although it's reciprocal in xi. Is the fourth regression equation linear regression? No. The last regression equation is not linear regression. Why? Because it is not linear in the parameters. If you look at the last regression equation, it is not linear in the parameters. Why? Because instead of b2 we are having b2 square. This is not linear in B2. Not linear in B2. That means the last regression equation is not a linear regression. So I can say this is not a linear regression. Why? Because it is not linear in parameters. Forget about the xi. It's not linear in parameters. So not a linear regression. Whereas these three equations are linear regressions. Because they are linear in parameters, forget about the xi's. So guys, this is where I intend to stop in this particular lecture. Okay. I hope all students have enjoyed this lecture. What we have covered in this lecture is the concept. We have revised non-stochastic population regression function, which we had done in the last lecture. We have started with stochastic population regression function. We defined the disturbance variable. Then we talked about the sample regression function, non-stochastic and stochastic. And then we have looked at the sample residual EI, okay, which is used to estimate the population disturbance variable UI. Okay, and then we have looked at the concept of linearity in variables versus linearity in parameters. And what we have learned is that when we talk about linear regression, it must be linear in parameters, B1 and B2. It may or it may not be linear in the variables, xi's. So guys, this is where I stop in this lecture. In the next lecture of Introductory Econometrics, we will talk about the method which will be used to estimate the population parameters capital B1 and capital B2. And that method is called ordinary least squares. So we will be discussing OLS, ordinary least squares, in the next lecture of Introductory Econometrics. So I hope all students have enjoyed this lecture. Any doubt, you can unmute your mic and ask, or you can call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop.